Hello guys, today we'll be talking about transformations of functions, especially quadratics, or most of our examples are going to be with quadratics, but these can work with many other functions, such as like all the 12 basic functions. And so to start, you have a parent function, which would be one of the 12 basic functions that we learned about before. For this video, we'll be using the quadratic function, and this should be the most prevalent in all your classes. And that is the parent function of the quadratic. And to this parent function, you can apply different transformations into this form, which is a times x over b minus h squared plus k. And hopefully this should be familiar. This is very similar to vertex form, and actually basically it is vertex form. And you have three different types of transformations. The first one is translations, which are rigid transformations, meaning they don't change the shape of the graph at all. And this means they either move up, down, left, or right. And these changes occur because h and k changes, so these are translations. And dilations are when the graph does change shape, they are no longer rigid transformations, and they're due to a and b, and they sort of change the how wide and skinny the graph is. So like if you have this is the parent function, x squared, so you can make it skinnier or you can make it wider, and that's what dilations are. And reflections are when you can reflect across the x and y axis, and y-axis reflection looks like this, where you'd have a function here and it reflects horizontally across the y-axis. So it kind of like flips across the y-axis and you get like a similar function. You get the same exact function but in a different quadrant. And similarly for reflecting across the x-axis, you can have a function here and it'll flip across the x-axis and look like this. So you kind of just, for the x, you turn it, you flip it, and then you move the same distance away from the x-axis. And this is, we'll talk about how this is seen in the functions later. We can also apply these into the form f of x. So you have f of x equals x squared, and then you can apply these modifiers like a, b, h, and k. You can modify it here where you have like f of x plus h, or x minus h, or f of x plus k, or f of x over b, and then f of a times f of x. And you can see this is the x term, so anything that happens in the x term changes x, or changes like how it changes x basically like horizontally. And then a and k are outside of the x term, so they change y. Now moving on to translations. So translations are, once again, they go up, down, left, and right, and they don't change the shape of the quadratic. So going back to this form, y equals, or f of x equals a times x minus h squared plus k. We can see that h and k affect our translations. And since, first of all, we do left and right, which changes x. So x is left and right, we know that, horizontal, and y is up and down, so vertical. So a change in x means that it's inside of this x term, which is defined by the parentheses. And this means that it goes left and right, and you notice the negative here. This means that basically whatever you see, like if you see x minus 3, this means that it goes right 3 instead of left 3 because of the negative. And vice versa, x plus 3 would go left 3. Now here for y, you can see k is outside of the parentheses, so it changes y, and it's a vertical translation. There's a plus here, so it's basically what you see. So if k equals 3, so x squared plus 3, you would go up 3, not down 3. And x squared minus 3, you go down 3. So this is pretty self-explanatory on a graph. You can have x squared is the parent function, and you have, let's just say, x plus 3 minus 3, x plus 3 squared minus 3, and we can graph this out. So this would go, since it's plus 3, it goes left 3, and then it's minus 3, it goes down 3. And hopefully you can see this is vertex form, so the vertex should be at negative 3, 3, and it opens up. And that's it for translations. Okay, so dilations are basically when the graph either shrinks, it gets thinner, or it widens. And going back to the equation, equals a times x over b minus h plus k squared. We can actually see that a and b cause these dilations. A is a vertical dilation, and B is a horizontal dilation because it's inside of the x term. So since vertical dilations are much simpler, we'll go over that first. So vertical dilations are split between stretches and shrinks, and that's for both even horizontal dilations. And here you can have you have a stretch when the absolute value of a is greater than 1. And you can think of this almost like an exponential function. If the absolute value of a is between 0 and 1, there's a shrink. So this is a stretch. This is a vertical stretch, and then this is a vertical shrink. And if you think about this, this makes sense because when you have an a here, you're actually multiplying this whole thing. When you have an a that's greater than 1, you're multiplying this whole thing, so you're making it larger. So y grows faster. So this means for a lower value of x, you have a higher value of y. So what do you think this will do to the equation? So here, this is our normal equation. If y suddenly grows faster, for example, let's say this is 1, so at 1, the y value will be larger than the parent function. So the function will become skinnier, and it will be stretched up. So like think of it as like if you have something that's loose and then you stretch it, it'll become tighter. So it's becoming thinner. So that's what a vertical stretch does. And then a horizontal shrink does the opposite. I mean vertical shrink, not horizontal, sorry. Does the opposite, where it makes the function wider. And this makes sense again because y grows slower, right? Because if you multiply something by something that's lower than 1, in between 0 and 1, you get a lower number. So like 1/2 times 3 is 1.5, which is lower than 3, right? So this means y grows slower. So for a value, if this would be our parent function, for a value of 1, our y would be lower. So it would be more stretched out. Or it would be wider, not stretched out. So you're kind of like shrinking the y-axis down. I can do an example. Let's say y equals 2 times x plus 1 squared. So we can draw a graph here, and we go left 1. And then since this would be our normal parent function, we actually stretch it and make it, since this is a vertical stretch, because absolute value of a is greater than 1, this is a stretch by a factor of 2, the function becomes skinnier. So these are horizontal dilations, and this deals with b. And as you can see, this is inside the x term, so it's technically horizontal, not vertical, because we know x deals with horizontal. And if you think about it, this could technically be factored out and become an a. And so that means basically vertical and horizontal dilations are the same. And I urge you to always factor it out. If you have a b here, always factor it out to make it an a, because as you can see, if you have x over 2, or usually you'd say 1/2 times x minus 1 squared, this actually doesn't mean that you actually move by -1. You don't move right 1 because there's a 1/2 here. You would have to multiply this out. So you'd do 1/2 times x minus 2, all squared. So then you do 1/4 times x minus 2 squared. So you actually move by 2 to the right. So that's why, and there's a vertical shrink by 1/4. That's why I wouldn't advise you to deal with horizontal ones, because you can't actually translate the graph if you have something in the h value. So I would almost always factor it out. However, if they do ask you for horizontal dilations, you have to say when b is greater than 1, there's a horizontal shrink, and that basically means the graph becomes skinnier. And if b is in between 0 and 1, there's a horizontal stretch, and the graph becomes wider. However, once again, I don't advise you to actually deal with horizontal stretches, and instead factor it out by first factoring out the b value, while keeping it. Remember to keep it. If you have x over b minus h squared, you have to first factor out the 1 over b times x minus b times h. So when we multiply b times bh, we get h. And this is all still squared. So you actually have to do 1 over b squared. That would be your final vertical shift, vertical dilation. Sorry. Okay, now moving on to reflections. This is where you either reflect across the x and y axis for translations. And this can be manipulated through a and b in the actual equation, and then using the f of x notation, or function notation, or whatever you want to call it, negative f of x is a reflection across the x-axis, and then f of negative x is a reflection across the y-axis. And if you think about it, this sort of makes sense, because when you're reflecting across the x-axis, you have, let's just say you have a quadratic here. You're reflecting, you're making every single y value negative, right? And you can see that like this whole function represents your output, which is your y value. So by making everything negative, you're basically just putting everything into the negative side of the graph, and that basically just makes every y value negative. So you're flipping it on its head and going the same distance from the origin. Similarly for reflecting, and you can also see that it's reflecting across the x-axis. Similarly for f of negative x, you have where it's reflecting across the y-axis, which also makes sense, because if you have a function here, you're basically making every single x value negative. So you're keeping the y values, so it should look the same, like shape-wise and like also direction-wise, but you're kind of flipping it over the x-axis. So if you're saying like, oh, here it's getting smaller, so here it's getting smaller but on the negative side. It's getting a smaller absolute value but on the negative side, and here it's getting a larger absolute value but on the positive, on the negative side as well. So it basically is the same function, just in a different quadrant across the y-axis. And in a real function, this can be represented through the a and b values. The a value sort of represents a reflection across the x-axis, because once again you're not inside of the x term, right? As you can see here, you're outside of it, so you're sort of manipulating y. That means it's similar to negative f of x. On the other hand, b, having a negative b value, is a this is it. Negative a value represents a reflection across the x-axis, and then having a negative b value represents a reflection across the y-axis. Now, don't get confused, because even though these do represent reflections, when you have it in an actual function, it functions slightly differently than these two, because you have to follow PEMDAS doing any sort of transformation. So let's say we have the function 1 times x plus 3 squared minus 2. So you go here, right? And then you go left 3, down 2, and then you'd open up, right? What you would do, you wouldn't actually reflect it across the x-axis and go down here, because you have to follow PEMDAS. You have to, if you make this negative, you can't just do that, because you have to follow PEMDAS. What you do is you actually go left 3, because it's inside of the parentheses, right? And then you multiply it, you make it negative. So instead of going here, instead of going up like this, you actually go down, right? Because it's now negative, and you're flipping it across the x-axis. You're making every y value, every positive y value negative, or negative value positive. So you see that, wow, okay, now it's going down, and now you go down 2. So 1, 2, and here. So it basically, when you're flipping, when you have a negative here, don't think flipping across the x-axis. Just think, oh, I'm just gonna find the vertex without the a value, and then I'm gonna flip it from there. So instead of doing all of this complicated thing, you can just find the original function, which we said was around here, and then just flip it down. We can see this on Desmos, actually, when you have f of x squared plus 3, let's say, because that's a better example. If we make the a value negative, g of x equals x squared plus 3, we see it's the same function. And then we make it negative, it doesn't flip across the x-axis, it actually just flips from the vertex, it flips down because of PEMDAS. Now, you can also flip across different, stuff that aren't the x and y axis. And there are some rules for that. There's no great visual rule, but there are rules. So if you're reflecting, you can reflect across y equals x, and then y equals negative x. So these two lines. So this is y equals x, and this would be y equals negative x. There are some rules for points. For y equals x, you basically just go from x comma y. If you have a point on a function called xy, that point on the reflected function is going to be y comma x. Sorry, it's not negative. Similarly, for y equals negative x, it's basically the same thing. The point x comma y would be negative y comma negative x on the reflected function. This is used actually in things called inverses, which you will learn about later, because an inverse is basically just a reflection across y equals x. So this is useful when you have, like, for example, you have a quadratic with the point 1, comma 2. That contains the point 1, comma 2. And you're reflecting across so this point on the corresponding reflection would be 2, comma 1 in the reflected axis. And that is it for reflections. Now we can put it all together and actually do an example problem with a lot of the transformations we just learned in it. So first off, you have to list all the transformations in order, so in PEMDAS order. And draw a rough sketch. So you don't have to like calculate any of the points, but draw a rough sketch. Pause the video and try this on your own. I'll walk through it now. So first we can list all the transformations from the parent function x squared. And we can see that first, we can see that there's a plus 3 here. And since it's opposite, that means it goes left 3. And then we can see that there's a negative 4 here. So it first reflects across the y-axis. And then there's a vertical stretch by 4, since a, which equals 4, is greater than 1, which means the graph gets skinnier, right? And then there's a translation up 1. So this would look like this, where we have here, this is the x-axis, this is y-axis. Make sure to label all your axes when you're doing this on a test or in class. And then here we would have the parent function would be this. I'm going to draw this in like dotted lines. So this would be left 3 first. So 1, 2, 3. Then reflecting across the x-axis, sorry, not y-axis. That would mean it would go down, right? And then there's a vertical stretch by 4, so it gets skinnier, right? From this function, and then up 1, so up here. So the final function should look something like this, and we can confirm that in Desmos, and you can see here, there it's above 0, above the x-axis, and it points down, and it is in fact slimmer than x squared. We have x squared in the green, and then our actual function in the blue. Now this entire video I've basically been reviewing like transformations of quadratics, but these can work with most of the other 12 functions that you guys know, especially the absolute value function, which is very similar to the quadratic. Like quadratic looks like this, and an absolute value just looks like a quadratic but like sharp, right? So we can try doing the same thing we just did but with an absolute value function. And this is very, very similar. You can see here, you can follow PEMDAS again. So we can see that the closest thing to the x in the parentheses is the negative 1. And we know that it's opposite, so it's translate right 1. And then now we're out of the parentheses. The next closest thing, PEMDAS, multiplication. So we're multiplying by negative, so that means we're reflecting across the x-axis, since this is also outside of the x term. And then we're going down 5. So for graphing this, you should know your parent function. What does absolute value of x look like? Which this is y, x, and then draw this in a dotted line so we can see that. And then we apply the transformations we just listed. So we go right 1, and then we reflect across the x-axis, so we would go here, and then we go down 5. This will be our vertex, and this is our function. And we can see this, we can see that this is actually very similar. It's actually exactly the same as what we drew. This is our parent function, y equals absolute value of x, and this is our transformed function with the vertex 1, comma, -5, which we found, and it points down.